Welcome back. We are delving into a very interesting type of data right now called survival data or time to event data. Very popular way to design a medical study. Can get a little bit confusing because there's some specialness that you need to interpret it. So we're going to walk through that right now. I'm going to explain what survival data is and what makes it so unique. Talk a bit about survival analysis and give you the keys to interpreting survival data in medical studies. But sometimes it's easier not to talk about people. It's easier to talk about TV shows. Do you remember that TV show Firefly?
Keep the money. Use it to buy a funeral. It doesn't matter where you go or how far you fly. I will hunt you down, and the last thing you see will be my blade. Dark.
Now this is all the money Mr. gave us in advance.
I'm good. Best thing for everyone. I'm right there with you.
Firefly was just a great show. It left us after one season. It did not survive very long. Television shows, like people, have a lifespan, but it's sort of unique how that lifespan dictates their chances of getting another season. And I'm going to show you some television data that looks an awful lot like human data in just a second. But before we get there, we have to talk about the fact that survival data is not normal. Remember we talked about what makes data normal, right? Bell-shaped, that sort of bell curve, okay? Survival data does not look like this, okay? The age of death is not normally distributed. If it looked like this, it would be very strange. It would sort of suggest that, people kind of come up to age 60 and a bunch of them die, and then there's some people who live longer. No, of course, it does not look like this. No, death data looks like this. It's not bell-shaped at all. Very few people die in their middle years of life, and then there's kind of this big acceleration towards the end of life. So all of those statistical tests that we have to compare normal data and things like that are just not going to work. Now, why is this? Why is survival data so different than everything else in medicine, much of which follows this normal distribution pattern? Well, the reason is that survivors are more likely to survive. And I don't know if that sounds like a tautology or not to you, but think about it for a minute. These are the current life expectancy statistics for various age groups. So when you're born in the United States, if you're a woman, your life expectancy is 81.1 years right now. Respectable, not necessarily as good as it could be for a developed Western country, but that's okay. Now, if you're a 50-year-old woman, your life expectancy is to live to 83.24 years, so a little bit older. Why? Why are you more likely to live to longer years if you made it to age 50? Well, the answer is that survivors survive. You've made it that far. You've made it 50 years. There's something special about you, okay? And you can take this to extremes. If you live to age 80 as a woman in the United States, your life expectancy is to live another 10 years till you're about 90. If you live to 90, your life expectancy is to live another 5 years. So at any point in time, the people who are still left are the best of the best, right? The strong survive. So that's why survival data has this really sort of unique characteristic. Now, there's a lot of different ways to graphically represent this, but the most common one is called the Kaplan-Meier curve. And I'll show you an example here that looks at the risk of death from smoking. If you take home anything from this class, it'll probably be that you shouldn't smoke cigarettes. Not surprising. So the Kaplan-Meier curve says, we're going to start with a population where everyone's alive. So here's the survival rate, 100%. That's the top. And then we're going to follow over time and see how many people are left alive, essentially. Now, this study looked at people at age 35, so you had to at least be age 35 to get into the study. So we have 100%, and then it divided by smokers versus non-smokers. The solid line is the non-smokers, and you can see that over time we're losing these people, right? People are dying, and by the time you get to 99 years old, we only have 2% left. The smokers follow a similar pattern. Now, in the end, we all end up dead, right? Like, that's another kind of unique thing about survival analysis. As of yet, no one has lived forever. Knock on wood, some of us will. but as of now, everybody dies. So if you did a study that you were just asking, what percent of people survived, well, if you do the study long enough, the answer is always 0. But you probably want to be on this curve, not this curve, right? Because you can see that there's space between here. And there's about a 10-year difference at the median at about 50% survival, which suggests that you will live longer on average if you don't smoke than if you smoke. Okay, so another sort of special thing about survival data, and a lot of our statistics leverage the space between these lines and the relative difference between these lines at various time points to tell us what the risk of something like smoking is. Let's get back to TV shows because that's a lot more fun than smoking and death. So TV show survival is actually very much like human survival because, as you can imagine, your chance of getting renewed for another season is very much tied to how many prior seasons you've had. Now, you may think that the more seasons you've had, the less likely you are to be renewed for another season. That is not true, because if you've had 10 seasons, you're a pretty successful show, right? You're doing well. The chances are you're gonna get renewed for another season. So what I've graphed out here are some of the longest running television shows. In the IMDb database, you can see Mr. Rogers' Neighborhood had a pretty good run there. Evening at the Pops was pretty good. I think Masterpiece Theater was pretty strong. And then I created a Kaplan-Meier curve. Now, I only included shows that were on for 10 years at least, because there's just too many. Now, of the shows that have been on for 10 years, so what you can see is the beginning of this Kaplan-Meier curve is perfectly flat because I only included shows that were around for 10 years. So for the first 10 years of time, 100% of shows survive. And then you see a very similar Kaplan-Meier curve to you see for people who smoke. The shows start falling off. The shows start getting canceled. There are some that are still going out to 40, 50, 60 years. I can then stratify that analysis by various exposures. And in this case, the exposure I picked was the station that it's on, NBC, ABC, or CBS. And you can see that there's differences here. These lines sort of spread out. And so just by looking at the graph, you can see, for example, that the green line here, which is ABC, is a bit higher, has a bit better survival than the orange line, which is CBS. So if you were a show, all else being equal, and you wanted to survive as long as possible, you would want to be on ABC. Now, we can quantify that with a measure called the hazard ratio. Now, I've mentioned that before, but I'll just remind you that a hazard ratio is the timed version of a risk ratio or a relative risk. So to put some hard numbers to it, compared to other television channels, ABC has a hazard ratio for cancellation of 1.8. That means, compared to that brown line, which does pretty well, the other channels, ABC, which is the green line, has an 80% higher rate of cancellation at any given time point. So note I said any given time point. The hazard ratio tells you across the entire lifespan how much is your risk of being canceled increased. So it sort of integrates all those different time points, which is a really powerful way to do it. Now, this assumes that ABC just always has an 80% higher risk than other channels of canceling a show. They just like to cancel. They got an itchy canceling finger. It doesn't matter how long the show's been running. That is an assumption. It's a statistical assumption. It's actually called the proportional hazards assumption. You don't have to remember that, but it means that that excess risk is constant over time. It's just, even if you're 10 years out, you're just 80% more likely to be canceled than a 10-year-old show on another channel. In this case, it pretty much holds true. And ABC has a hazard ratio of 1.8, CBS 2.0, NBC 2.5 compared to our reference standard. So expressing things in a hazard ratio takes these graphs and puts them into a single number that you can use to express risk. So how does this work in a medical study? I'll just show you a couple. Randomized trials often use these survival analyses. Instead of just saying, what percent of people died at a year, they'll say, how long did people live? That captures a little bit more data, right? Because maybe, in a very terrible disease, maybe maybe everyone is dead within 10 years or something like that. But you want to capture that who lived longer aspect of things. So this was a study in JAMA that looked at prone positioning for respiratory failure. Prone positioning is face down positioning. don't often see people in the hospital face down in their bed, but there at one point was a lot of interest in doing this to improve how people were breathing. And what you can see here is a Kaplan-Meier curve of the prone positioning versus the supine positioning. This was a randomized trial. They flipped a coin to see who was on their back versus who was on their stomach. You don't need a randomized trial for survival analysis, but this was a randomized trial. And you can see these lines basically overlap. And the hazard ratio was essentially 1. There was no benefit or harm to prone versus supine positioning in this particular study. Now, there are these numbers at the bottom of a Kaplan-Meier curve that confuse a lot of people, so I want to take a minute just to talk about them. So this is another randomized trial looking at a drug called cediranib for ovarian cancer. Ovarian cancer, obviously a cancer with very high mortality rate, unfortunately, even despite some significant developments. What you can see here are the Kaplan-Meier curves starting at 100% survival, like they always do, and going out, the units here on the x-axis are months. Okay, so 50% survival is happening here around 24 months. So 50% of people are dead in this study after 2 years. That's not great. Ovarian cancer is a very serious cancer. And what you can see are 3 different lines. You've got a reference group, a concurrent therapy group, and a concurrent maintenance group. And I'm not going to go through what these randomized groups were for. They're just different types of treatment that they were giving them. And you can sort of see that the blue line did a little bit better. I mean, no one does well. But I wanted to pick this one because I wanted to talk to you about this number at risk. So the number at risk tells you how many patients are around at a given time point to be evaluated. So at the beginning of the trial, you can see there are 118 patients in Arm A, 174 in Arm B, and 164 in Arm C. And that's fine. And as you go across, you can see these numbers get progressively lower. And in fact, when you're out at 36 months, you see 8 patients in Arm A, 16 in Arm B, 12 in Arm C. So we went from 118 in Arm A to 8 in Arm A. 90% of the students I've talked to think that that means that we started at 118, we went down to 8, that means 110 people died, okay? That is not true. If 110 people out of 118 people died, that's almost 100% death, and we'd be down at 0, right, by 36 months, and we're not. This reflects the number of patients that we have data on. Some of them might be dead, some of them might be alive. It's the number of patients that we have followed to this point. Now, so we might have lost patients to follow-up, like we talked about in some of the other lectures. Just kind of lose track of people. But more importantly, you have to realize that when you're conducting a study like this, you don't enroll all 100 people on like January 1st and follow them for 2 years. No, you enroll like 2 people on January 1st, and then you enroll a couple of people the next day, and then you enroll 3 people 2 weeks later, and so on. So everyone's entering the study at different time points. And you might conclude the study, and some of your people are only 19 months out. They've just only been treated for 19 months. So you can only use their data for 19 months. You don't know what's going to happen to them in month 20. So you can use the fact that they're alive at month 19, but after month 19, you can't use them at all. So the number at risk doesn't it reflects not only people who have died or experienced the outcome, but also people who are lost to follow-up or people just who haven't been followed to that time point yet. So don't get too hung up on this. The only importance of the number at risk is it gives you a sense of the imprecision of your measurement. If you only have, a few people left this far out, you just can't be very precise about the effects of a given treatment. So oftentimes you're going to be looking more at the midpoints of the Kaplan-Meier curve when there's enough data to make some real assessments of what's going on. Now survival, I've kept calling it survival. It doesn't have to mean survival. It can be time to event. Okay, so the event could be death, but the event could be a heart attack or getting married or any discrete thing that can happen. We can just say, how long does it take until you buy a new car, right? It's all the same type of analysis. Here are your take-home points. Time to event data is special. It needs to be analyzed using statistics that understand that the longer people survive, the longer they survive. Comparisons are usually made with the hazard ratio. It's just like a relative risk. Interpret it very much the same way. The number at risk goes down, both because people experience an event and people are lost to follow-up. So don't get too scared when you see only 2 people 10 years out in your number at risk. It may just mean that not everyone has reached 10 years yet. Catch you next time.